let's go on back to the extra practice problems. And they are found on page 622. Number 1, nitric acid is manufactured by the following reactions. So we have 3NO2 plus H2O yields 2HNO3 plus NO. Now it says to us how many grams of nitrogen dioxide, which is here, are required to produce, and we're looking at over here, 2945 kilograms, so I'm going to go times 10 to the third grams. Okay, there's excess water, so we're going to ignore that. And so let's start with, I should have done this on the top, I'm sorry. 2945 times 10 to the third grams. That way we have more room, question mark grams. Okay, did I put that right? Yes. All right. So we're going to start where we have a number. 2945 times 10 to the third grams HNO3 times line. Remember, we're going to have to go from grams to moles, across the mole bridge, and back to grams. But if you just follow this, HNO3, now you have to go to the moles, and you can only go to the moles of the same thing. If you got grams of one, it has to be moles of the same thing, same substance. Then we want to go across the mole bridge. So I'm going to go moles of HNO3, and I want to get to moles of NO2. Then I want to go from the moles of NO2, I want to go back to the grams of NO2. And that way I'll be where I need to be. Now, if you're not comfortable putting them all together yet, that's okay. You can do this one step at a time. And that's fine. You would do this step, get a number, then you go to this step, get a number, and then you go to this step and get a number. We know that in 1 mole of this, when you add up nitrogen's 14, 3 times 16 plus the 1.01, it's going to give you 63.0 grams. We get these numbers from our balanced chemical equation. Okay, we know 1 mole of this is 14 plus 32, which is 46. I know you're thinking 14 plus 32, she should be able to do it in her head. I'm tired, just let it go. Okay, we have 3 significant figures, 3, 4. So our answer is going to be in 3 significant figures. And now if you do it piece by piece, I'm going to show you. The answer is 3.226 times 10 to the 6th grams of nitrogen dioxide. If I do it all together, I want to see if it's different. 3 times 46 equals, divided by 2, divided by 63 equals, and the answer I got out of here, 3 significant figures, 3.23. Nope, I got to need 4 significant figures. How can that be? No, it has to be in 3 significant figures. There's 3 here. There's 3 here. It's got to be in 3 significant figures. I'm so sorry. And that's actually, it's close, but it's actually going to be the same thing, times 10 to the 6th. That's good. Okay. If we had to go out to the 4 significant figure, that's where it would have varied. Okay. Number 2, tungsten metal, W, is produced by the following reaction. And we have WO3 plus 3H2 yields tungsten plus 3 waters. There we go. Okay, how many grams of tungsten are made from that much of hydrogen in excess of this? So the hydrogen is 2.0 times 10 to the 6th grams. Okay, so we're going to go, I'm going to move over here so I have plenty of room. 2.0 times 10 to the 6th grams of H2 times line. We're going to go from grams to moles, moles to moles, moles to grams. So whatever's here always goes here, and I've got to go to moles of the same thing. Now whatever's here has to go here, but I'm going across the mole bridge. And then whatever's here has to go here. And now I get to go to the grams of the same thing. Whoops. I can do it as long as it's the same thing, can't I? Okay. What goes here? Hydrogen gets a 3. Tungsten gets a 1. This gets a 1, and I know that this is 2.02. This gets a 1, and you look up tungsten on your chart, and it's heavy. It's 183.9. And that's going to give you two significant figures, 6.1 times 10 to the 7th grams of tungsten. This will cancel, this will cancel, this will cancel, and you're left with what you want. Okay? And once again, you feel free to do these in steps, but this is how they do it in college, and this is how I'd like to teach you to do it so that you're able to do it when you get to college. Okay, two significant figures, because that's what we started with, was two significant figures. Number 3, how many grams of WO3 would be used in the above reaction under the conditions specified? Okay, well, let's go back and under the conditions specified. So we already had 2.0 times 10 to the 6th grams of hydrogen, only this time, and we already had the grams of hydrogen to the moles of hydrogen, 1, 2.02. But this time we're going to something different. This time they want us to go to WO3, which I already erased it, but you can look at it in your book. Moles of WO3. And this is okay, so this is 3 hydrogens to one of those. All right. And then you're going to times line moles of WO3 to grams of WO3. One of these, and you add up 3 times 16 plus the tungsten, which is 183.9, which is going to give you 231.9. That's heavy. And then when you multiply this all together, it's going to give you two significant figures because of your starting number, 7.7, times 10 to the 7th grams of WO3. Let's go to number 4. Carbon tetrachloride is made according to the following reaction. So we have CS2 plus 3Cl2 yields CCl4 plus S2Cl2. We are told how many grams of CS2 are needed to make 8 kilograms of carbon tetrachloride. So I'm going to convert that into grams because I know I'm going to have to, so what the heck. All right, so we start with where we have numbers and drive to where we have a question mark. First, we're going to take the grams to moles. So grams to moles. Then we're going to take and go across the mole bridge. Going to CS2. And then, and it's always whatever's here goes here. Whatever's here goes here. So whatever's here goes here. And now we can go to grams, which is what we're looking for, right? And then you know where to put your numbers. So we have 1 mole of this, and you add this up, and it's going to give you 154.0. If you look here, we have a 1-to-1 relationship. And then if you add this up, it's going to give you 76.2, 1 mole of that. And that's going to give us 4.0 times 10 to the 3rd grams of CS2. Okay? Yeah, you really have to kind of keep up with this. All right, but it's the same thing over and over again. To make a phosphorus fertilizer, agricultural companies use the following reaction. And I am going to cheat because my arm is really starting to hurt. So Ca, get the glasses, Ca3P2O8 plus XS yields CaH4P2O8 plus, okay. So we have here the things we need. And I want you to notice it's a 1-to-1 relationship. So we're told here that we have 5.000 times 10 to the third, that's a 0, times 10 to the third grams. And we're reacting it with excess of those. How much fertilizer can be made? So we want to know how much fertilizer can be made. So we're going to take 5.000 times 10 to the third grams, Ca3P2O8. That's an 8 times line. Grams, Ca3P2O8. We're going to go to moles, just like we have been doing. Times line. Now we've gone from grams to moles. We want to go from moles to moles to get over here. So we're going to go moles, whatever's here. And we're going to go over to here because we can. And that's where we are trying to get to. Then, whatever's here always goes here. And grams, I'm going to cheat here and write fertilizer because my right arm is killing me. Okay, we know this is a 1-to-1. We're going to add this up. So it's 3 times calcium plus 2 times phosphorus plus 8 times 16 for the oxygen is going to give us 310.3. And then when you add up the fertilizer, it's 234.1. And so 4 significant figures, yes, we have. If you do it this way, you end up with 3,772 grams of fertilizer. If you ended up doing it piece by piece, you would get 3,771 grams of fertilizer. Both are acceptable, have the right number of significant figures, and so that it'll come out. But it just depends on how you chose to set it up, whether you did it in pieces or whether you, I'm going to use my left arm because my right arm's dying. Whether you did it in pieces or whether you did it all in one big step like I do. So that's up to you. Shame I can't write with my left arm. I'm not good at that. Maybe some of you can. Number 6, in the following reaction, magnesium, water, okay. What mass has magnesium must you use to get that much magnesium hydroxide? Okay, so we have Mg plus 2 waters yields magnesium hydroxide plus hydrogen gas. Okay, what is the mass of magnesium that you must use to get 2.8 times 10 to the 4th grams? There we go. Okay, so we start where we have no question mark and we drive to where we have a question mark. We have to take our grams and go to moles. Whatever's here has to go down here. Now we're going to moles of the same thing. That's the only thing you can do. So we're going to come back to that. Then we go across the mole bridge. Wow, we have a 1-to-1 relationship there. So it's going to be 1 and 1. I'm going to save my arm a little trouble. But this is going to be moles of that, and this is going to be moles of magnesium. Oh, I'm going to write it. I just can't do it. Okay. And then we have moles of magnesium, and we're going to go to grams of magnesium. Okay. And magnesium, if you look on your chart, it weighs 24.3 grams. And then if you add it up with the hydroxide, it ends up being 58.3 grams. If you put it all in your calculator, you want to have 2 significant figures in your answer. It's going to be 1.2 times 10 to the 4th grams of magnesium. 1.2 times 10 to the 4th grams of magnesium. Let's see. Which of the following are empirical formulas? Now remember, the empirical formula is the simplest whole number ratio. So A is SO3. Can you divide it through by anything? No. So A is empirical. B, K2S2O3. Right, that's empirical too. C, C6H12O6. Wow, it's glucose. We definitely can divide that through by 6, can't we? So that is not an empirical formula. P2H4. We can divide that through by 2, so it is not an empirical formula. Number 8, Decomposition of 200 grams of a dark green powder yields 79 grams of potassium, 55 grams of magnesium, and an unknown amount of oxygen. What is the empirical formula? Oh boy, let's have some fun with this. Okay, so we have something that's made up of K and manganese, oxygen, Z. We're going to decompose it, and so that's going to be K plus Mn, isn't it? Yep, sorry. I bet you guys were waiting for that, huh? Manganese plus oxygen. Who gets the little twos? HNO group 7. Neither of these two are in group 7. Then we are told that this is 79.4 grams. And this is 55.8 grams, but they didn't tell us how much oxygen. But you know what they did tell us? They told us that the original sample was 200 grams. 200 grams. So if we add those two numbers up, 79.4 plus 55.8 equals, we add these two numbers up and it gives us 135.2. So we know that the oxygen has to be what's left, don't we? Because of the law of mass conservation. I'm just going to add those two numbers up one more time to make sure that I did it correctly. Yep. Okay, so we got 200 minus 135.2 equals 64.8 grams. 64.8 grams. Okay. Now, so this is 64.8 grams. So now we go to how many moles of each there are. Grams of potassium times line, grams of potassium, moles of potassium. We know that in 1 mole there is, oh, got to get my glasses. Sorry, guys. There we go. 39.1. And so that's going to end up giving us 2.03 moles of potassium. Then we go 55.8 grams of manganese times line, grams of manganese, moles of manganese. 1 mole, look on my chart, and it's 54.9. And so that's going to end up giving me 1.02 moles of manganese. And then I have 64.8 grams of oxygen times line, grams of oxygen, moles of oxygen. And 1 mole, there's 32.0. And so when we divide that, it's going to give you 2.03 moles of oxygen. Now, obviously, we can't use these numbers because they're not whole numbers in here. So we take the smallest of the 3, which is 1.02, and we divide all of them by the smallest of the 3. That's going to give us 1 mole of manganese, so we're going to leave that alone. That's going to give us 2 moles of O2, so we're going to put our 2 up here, and that's going to give me 2 moles of potassium, so I'm going to put a 2 over here. So we've taken it to the moles, because it wasn't a whole number, we divided everybody through by the lowest whole number, and then we went ahead and we put them into our equation. So now we can go back over here, and we balance this equation, so the potassium gets a 2, the manganese gets a 1, and the oxygen gets a 4. So we have K2MnO4. Now the question was, what is the empirical formula? Well, that is an empirical formula, isn't it? Because you can't divide it through by anything, so that would be our answer. Number 9, the mass of the molecule above is 197.1 grams, or AMUs, your choice. I'm going to use grams. What is the molecular formula? So 197.1, I'm going to put grams, and we had that it was K2MnO4. So you go on your chart, and potassium, 2 potassiums at 39.1. The manganese was 54.9, and 4 times the oxygens, these are all in grams. I'm going to use grams rather than AMUs. My choice, It works either way. Believe it or not, if you add that all up, it's 197.1 grams, and so it's a 1-to-1, so that is the molecular formula. All right, let's do number 10. Number 10. A compound has an empirical formula of CH2O. Its molecular formula is, its molar mass is 60 AMUs. What is its molecular formula? Okay, so we have CH2O, and we have its, I'm just more comfortable with grams, so you guys forgive me. You can use AMUs here if you want to. Okay, so we add this up. This is 12 grams plus 2 times 1.01 grams. Oops, sorry. Plus 16 grams, and that's going to actually give us 30 grams. And so when we divide this by 30 grams, it's going to give us 2. So the molecular formula, we would just multiply this through by 2. And so that would be your molecular formula. Okay. Stoichiometry, very, very important what you're learning. If you still are having difficulty with any of this, please go back and work the example problems and the on your own problems and the study guide and the extra practice problems again without looking at the answers to make sure that you're able to do this. Remember, you always go from grams to moles, moles to moles, moles to grams, because the only way you can get back and forth in an equation is through the mole bridge. So you're always going to have to go there. Remember, if you have grams over moles or moles over grams, it has to be the same substance. That's the only way that you can do that that's legal, because that's the only funky one that you can come up with. So that'll help you. Remember that whatever you're writing on the top, that's what has to go in the bottom of the next unit that you're going to be multiplying by. Remember to always start with where there's no question mark, so you put those numbers down and then times line, and then you just start driving to where there is a question mark. I think if you do that, you'll be okay. The empirical formulas, when you're figuring out, remember, empirical formula is in its lowest form, whole number form. The molecular formula is actually how many that are in the molecule, so that won't necessarily be in the lowest form. Remember that if you could do a decomposition reaction, you're just going to take the grams and go to moles. And that way, once you have the moles, you can put the stoichiometric coefficients in and you can work your way backwards so that you know what the actual empirical formula was for that. And then if they give you the molar mass, then you just add up the empirical mass and take the molar mass, divide it by the empirical mass. It'll tell you what to multiply by. And then you just multiply that by that. It's actually very logical. I really like this textbook. We're going to get through all these little silly things, and it's really good. The way I think it's very good the way that it's presented here. So study for this. Take Module 8 test. Read the first half of the next chapter, and have a Jesus-filled week.